Yeah, so the next section in your notes was for homework, and then we went over it in class. So it says Flora is boiling water on a stove. She turns the temperature dial up to high to boil the water. The water is boiling vigorously with large bubbles quickly forming and bursting at the surface. Flora then turns the dial of the stove down to low. The water is boiling gently, with smaller bubbles slowly forming and bursting at the surface. Flora wonders if the boiling temperature changes when she turns the dial. What would you tell Flora? Circle the best answer. And then we have three options. A, the boiling temperature is greater when the dial is set at high. B, the boiling temperature is greater when the dial is set at low. And C, the boiling temperature is the same at both settings. And so we just want to read through and see if we can find some key information. So when the temperature dial is on high, the water is boiling vigorously with large bubbles. Okay, and when it's down low, it's boiling gently with smaller bubbles. But what I would like to point out is that it's still boiling. Okay, and the only thing that's happening is whether or not it's boiling vigorously, which means a lot and really quickly, or gently, which is a little bit slower. And so if we think about it, we would say, okay, A says the boiling temperature is greater when the dial is set at high, and B says it's greater when it's set at low. Well, I think that C is the correct answer. And so when we're explaining our thinking, okay, on these lines, we could say it is boiling at both settings, right? And that phase changes do not change temperature, right? If we go back to right above this, when we're looking at heating curves, we learned that with boiling, okay, this is my rough heating curve, boiling is happening right here, okay? And during boiling, the temperature does not change. So it might change how quickly it boils, right? We know if we put it on a high setting that the water will boil faster than if it was on low, but eventually it will start to vaporize and either boil, or you might see a lower boiling that doesn't really result in very many bubbles. But either way, the boiling temperature is going to stay the same. It stays flat. About how heat flows. So heat, which again, remember the symbol for heat is a Q. This is going to flow from objects with high energy, or hot objects, and it's going to flow to low energy objects. Oops, wrote the word energy two times. So low energy objects. So for example, if we have two pots, okay, so here's pot number one, and we have pot number two. Let's say pot number one is at 100 degrees Celsius and pot number two is at 20 degrees Celsius. Our temperature measures energy, average kinetic energy. So we would say that this has high average kinetic energy, and that this one has low average kinetic energy. And so one thing we know is that if we were to put these pots and pans, or these two pots, side by side to where they were touching, what would eventually happen to their temperature? Well, we know that eventually the 100 degrees Celsius pot would become 50 degrees, and the 20 degrees Celsius pot would also eventually become 50 degrees. And so what we see happen in this transition is there is an increase in average kinetic energy, and there's a decrease in average kinetic energy over here. And so what that shows us is that the energy that left pot number 1 had to go into pot number 2. So heat, which I'm going to do as a yellow line, flowed from the hot pot to the less hot pot. Now, one thing that my students have been hearing me say all week is that there is no such thing as cold. Okay, and I'm going to repeat that one more time. There is no such thing as cold. Now, some of you might be saying, well, I don't believe you. I don't agree with you. There is such thing as cold. I know when I feel cold. And if you said that exact word, I feel cold, then you're proving my point. Cold, as we use it, is a feeling, not a thing. Heat is energy. Heat moves in and out of something, and cold, by its very definition, is the lack of heat. So when you feel cold, what you really feel is the heat in your body leaving you. You feel a lack of heat. You feel your atoms in your body slowing down, okay, and you want to speed them back up, which is why when we start moving and we are active and engaging in exercise, we feel really warm because the atoms in our body are moving faster to accommodate that exercise. And so we want to talk about how heat flows, and in order to do that, we need to talk about the universe. And so the universe is made up of two kind of big, broad categories. You can say the system, which is anything you're looking at, and everything else is your surroundings. And so there are three types of systems that we want to look at. The first one is an open system. And in this open system, think about a cup of water. Okay, heat can go out of a cup of water and it can go into a cup of water. And the same thing with mass and matter. I can pour water out and I can pour water in when it's open. Now, if I put a lid on that cup of water and I close it, now there's this boundary here. Okay, and so with that boundary, heat can go in and out of a closed system. But if I pour it over, that lid will prevent water from coming out and it will prevent anything else from coming into it unless I open the lid, which would turn it into an open system. And then in an isolated system, we see that there are no arrows coming in and out, and so that means heat and matter cannot be moved. And so a good example of this is a thermos, okay? Or if you have one of those Yeti cups, we know that the cups that really trap in the heat or prevent heat from getting to our cold liquids can be kind of more expensive, right? And so the better of an isolator it is, or an insulator, if you remember hearing that word, insulators restrict the flow of heat. And so they're creating isolated systems. Okay, and so if these things are our system, then everything else all around it in the entire universe is the system. And so we have two big vocabulary words that we use to describe how heat flows. The first word that we use to describe how heat flows is endothermic. Now, endo sounds like the word in, and so it literally means for heat to flow into the system. Okay, which means if it's flowing into the system, it's coming from the surroundings. And so the more sciencey word for this is you might say that heat is absorbed into the system. Okay, and so this means that the system feels warmer, which means that you're going to see a temperature increase. Okay, now because we're using the word feels, Okay, we can use the words warmer and cooler, but remember there's no such thing as cold. Okay, no such thing as cold. Heat is moving in and out, but there is no such thing as cold. So the surroundings feel cooler because heat has left the surroundings to go into the system. So if my system is this box, okay, so we have system and everything else is the surroundings, okay, heat is flowing into the system, okay, and that would be endothermic. And so this means a container which is also part of the surroundings, okay, if our system is what is inside that container, then the container is going to feel cold to the touch, okay. Now, we know that in chemistry, we love graphs and charts, and we love chemical reactions. And so I want to kind of look at what this graph might look like. And so on the y-axis here, we have time, and on the, or excuse me, on the x-axis, we have time, and on the y-axis, we have energy. Sorry, I couldn't put it over there. And so what happens is in an endothermic reaction, there is an overall gain in energy. And so I'm just going to kind of draw the shape and then I'll explain it. So at the beginning of a chemical equation, you start off with your reactants. Okay, so you start off with your reactants. I'll just kind of write it over here on the right. And what happens is as you go on, you absorb some energy. And once you get to the top, that's called your activation energy, the amount of energy required to go from your reactants to the top of that hill, or the amount of energy to get a chemical reaction going. You release a little bit. And when you release those, you form the products, okay? But what we notice is that the absorption side is higher or greater than the releasing side. And so you gain more energy than you release. And so if you ignore this part, okay, they kind of cancel each other out, you notice that there is an overall gain in energy. And so here we might say Q, which remember is heat, positive, okay, and it's absorbed. Now, if we wanted to include energy in our equation over here, so we have reactants and we have products, the question becomes, would I write it on the reactant side or is energy a product? And so one easy way to look at that is if you look at where our excess energy is on this graph, it's right here, right? And what is it closest to? Well, it's closest to our reactants. So that means we could write reactants plus energy produce these products, okay? That you have to have that energy in order to really get going, okay? And so exothermic is essentially the opposite in every single way. So heat, instead of flowing into, heat flows out of the system. And so this means it is released. Okay, and so that means the system will feel cooler because heat is leaving it, so it feels the absence of that heat, and so that means you're going to see a temperature decrease. Okay, and so if we're seeing temperature decreases, these are, cooling curves are examples of exothermic reactions, and heating curves are examples of endothermic reactions. But that was a little side note. So our surroundings are going to feel warmer, okay, and we'll be able to measure that energy transfer by measuring the temperature. So the temperature will go up, and this means the container will feel hot to the touch, okay. And so the way its chemical equation would look like is you would have your reactants, okay, but now if energy is being released, that means energy is a product. It is something being produced and made from this reaction. And so if we look at its graph, which I'm not going to draw the labels, well, I guess I should. Let's practice good habits. So we have energy and we have time. It will look the opposite. So our reactants will be higher in energy than our products. Okay, and so my reactants and products, we see that we absorb some to get to our activation energy, and then we release a lot more. And so again, if we ignore the amount, that kind of cancels out. We see that if we draw an arrow from reactants to products, it goes down. And so this tells us that Q is negative and that it is released. And because that excess energy is next to the product side, I know that I can write it on the product side of the equation there. And let's look at some examples of situations where we might be asked to label them as being endo or exothermic. So if we look at burning natural gas, which is methane, that's what we use for our Bunsen burners, or gasoline, so things in your car, if you've ever seen gasoline light on fire, is it endo or exo? Well, if our system, okay, and that's going to be important for here, if our system is the natural gas or gasoline, well then it's burning. So it is releasing heat. We know that we feel flame and energy from the light, and so we feel all of that, and so it is exothermic. If you ever see anything burning, you know it's automatically exothermic, which means all combustion reactions are exothermic. And so when we look at baking a cake, well, if our cake is our system, then energy is going into the cake from the oven, and so it is endothermic. Now, if we were to change our point of view a little bit and say, well, what if my oven is the system, the thing that I'm studying or looking at? Then the oven is exothermic. It's releasing energy that is being absorbed by the cake, which is endothermic. Now, in order for melting ice, if ice is our system, in order for ice to melt, energy has to flow into the ice, and so it is endothermic. And you know that if you've ever held a piece of ice in your hand feels extremely cold, and that is because the heat is leaving your hand, leaving your body, and going into the ice in order to break those intermolecular forces and turn it into a liquid. And when we look at steam rising from a runner who has run a race, okay, we could look at this from several different perspectives. But if we say that the runner is our system, the runner has just run a race, and we see that steam is rising from them. Now, in order to turn the water that is around the runner in the air, and the sweat that is on their skin, in order to turn that into steam, okay, so in order to turn the sweat on their body into steam, they are going to have to be releasing a lot of heat to go from a liquid to a gas, and so this would be an exothermic reaction. So hopefully this clears up any misconceptions we might have had from class. And again, go to the next video for the next set of notes.